Okay, so in our last session, we covered some basic statistical measures of central tendency and measures of dispersion, mean, median, mode, range, standard deviation, right? We learned how to calculate them in some diagrams like box plots, histogram, bar graphs, right? We talked about all of that stuff. Now, there are some other concepts related to statistics that you also need to know about, and that's about sampling and making some inference using a sample. Okay, now this is another part of SAT that you do not know much about from O levels. So this is going to be new stuff, so make sure that you're paying attention. Now, in statistics, generally what we want to do is we want to make some predictions based on some given information. We want to estimate what the future would be like in different contexts. Like, for example, we can sometimes predict election results, right? We can take a sample of, let's say, 100,000 voters before an election and use that to predict what the election results would be when the actual voter turnout would be much more than that. So we just take a sample of, for example, 100,000 people, and based on that, we make an inference about 10 million people, right? Now, statistics allows us to do that. Now, when can we make such inferences? When the sample that we collect is random. So, for example, if you want to make some prediction about election results in Pakistan, you can't just take a sample from people from only Lahore or only Karachi or just one city or one area. It has to be random so that there's representation of people from all the different areas, all the different ethnicities, all the different religions, right? That will give you a better prediction. Your data set, your sample has to be random. Okay? So that's important. That whatever sample you take, it's important to remember it has to be a random sample, and then you can make an inference based on that. Okay. Now, these are some examples that statistics can be used for. For example, you can do a survey of college students to estimate how many of them live with roommates. So, for example, a university has 10,000 students. You want to understand if out of 10,000 of them, 7,000 live in hostels, let's say. Okay. You want to make an estimation of what percentage of those hostelites live with roommates and how many of them live alone. Okay. Now, it's very difficult to ask each one of those 7,000 students. You can't reach all of them. It will be too expensive as well to get access to all of them, right? So what you do is, out of those 7,000 people, you take a random sample of maybe 500 people, right? And based on that, you make an inference about all of those 7,000 people. Okay? That's called sampling. So that 500 number that we surveyed, that's a sample. And the 7,000 people that we wanted to say something about, that's our whole population. So using a sample, we make some prediction, make an estimation about the whole population. Okay? And this is something that we do a lot in statistics. Now, why is randomness important? Now, these are most theoretical concepts which are tested on SAT, so you need to make sure that you understand them well. Why is it important for a sample to be random? Because you want an equal chance of inclusion. So, for instance, if you are doing a survey of elections, let's go back to that. Now, it is possible that some remote area in Sindh, it has a completely different dynamic. The rest of the Pakistan might have, different preferences, and in those 2-3 areas in Sindh might have totally different preferences. You want to give those people an equal chance of inclusion as well, so that the results that you get at the end, they are more reliable. Okay? You can't just take sample from one particular area. And of course, when you do that, it minimizes any biases as well, and the results are going to be more accurate. So any statistical conclusion is only going to be valid if the sample is random. If it's not random, it's not a valid. You will not get a valid conclusion from that. Does that make sense? Okay. Now, one type of problem that you would get would be estimating the total number of people that you want to make an inference about. It's also called the population. So let's say this gym chain has 18,000 members. Now, you want to do a survey and figure out how many workout partners those members have. Now, it's difficult to ask each one of those 18,000 people. So what you do is you take a sample of 1,000 members. All right? Now, this is what the survey results are. Number of members, 350, workout partners, 0. Okay, so there are 350 out of those 1,000 people who have no workout partners. And then 300 of them have one workout partner, 200 have two partners, and 150 have 3 or more partners. Okay? This is the result of the survey that we did. Now, what's the total number of members that we can estimate that have 2 workout partners? So remember, we took a sample of 1,000 members. Out of them, 200 are saying they have 2 workout partners. Now, based on that result, can we estimate out of these 18,000 people, how many would have 2 workout partners? We can find this ratio, 200 over 800. That's 20%. So in our sample, 20% are saying that they have 2 workout partners. So in the whole population, we can just find out what the 20% of 18,000 is going to be. Okay, you can see what that is. 200 over 1,000 into 18,000, what does that give you? Sorry? 3,600. That's our estimate for the number of people out of those 18,000 people who have 2 workout partners. Is that okay? So that's how you can estimate something about the whole population using a sample. Now, can you say for sure that the total number of people who have 2 workout partners is going to be 3,600 out of 18,000? You can't say for sure because you haven't asked every one of them. You just took a sample of 1,000 people, right? And based on that, you're estimating that 3,600 out of 18,000 will have 2 workout partners. Now, it's not going to be very precise. There will be some margin of error. Okay? There can be some margin of error. So samples can never provide exact values of population. So there is going to be some margin of error in our estimate. Okay? Now, how we calculate these margins of errors, that's beyond the scope of SAT. You will study that when you go do your first statistics course in university. You just use softwares for that. Basically, there are functions behind that. You will be given margins of errors in the questions. You need to be able to interpret them. Okay? So this 3,600 number is going to come with a margin of error. Okay? Now let's see how that is going to look like. Let's look at this example. So a study on turtles estimates 35% of the population has spotted shells with a margin of error of 6%. What's the most appropriate conclusion about the proportion of the population with spotted shells? Who spotted shells? What do you think? So you are doing a study. You generally do that by taking a sample. Your estimate is that 35% of the population has spotted shells. But there's a margin of error in this estimation, and that margin of error is 6%. 6% means it could be 6% either way, plus minus 6%. Okay? Now, which of these conclusions is correct? Is the proportion exactly 0.35? No, we can't say for sure. It's plausible that the proportion is less than 0.29. Is it plausible the proportion is less than 2.29? Is it? Well, okay, let's skip it for a while. Let's look at the other options. It's not possible that the proportion is greater than 0.41. Is that correct? Okay. Let's look at the fourth option as well. It is plausible that the proportion is between 0.29 and 0.41. Now, this looks more correct, right? Because that's what we estimated here. 35% plus minus 6%. It says, which of these is the most appropriate conclusion? So looking at that margin of error, 35% plus minus 6%, that means the actual number is likely to be, between 29% and 41%. It's likely to be between this number. Is that okay? Now, this is going to be D, but now let's look at B and C as well. Why are they incorrect? It is plausible that the proportion is less than 0.49. Now, we are saying it's actually plausible that the proportion is 29% and 41%. It's more likely that the actual proportion is within this number. So B would be incorrect for that reason, that it's not the. It is possible that the actual number is less than 29%, but that's not what our result is saying. Our result is saying the proportion should be between 29% and 41%. That's most likely. Is that okay? But remember, it's just plausible. It is possible still that the actual proportion goes beyond this. It is possible. So if they are saying it's not possible that the proportion is greater than 0.41, we can't say that's correct. हो सकता है actual proportion 43% हो जाए. It is possible. We are saying it's unlikely because we are saying it's likely to be between 29% and 41%. And it's unlikely that it will be beyond those percentages, but it's still possible because you have just taken a sample. It is possible that the actual proportion is beyond what you have estimated. Does that make sense? So using a sample, you can just say something like this, that it's likely that the actual result is going to be within this range. But even though the probability of going outside that interval is low, there still might be a 1% chance or a 0.5% chance or a 0.1% chance that the actual proportion is beyond this. So we cannot say using this result that the proportion cannot be greater than 0.41. It is still possible. So that's why C is also incorrect. Is that okay? Any problems? Okay, let's have a look at this. A study estimates the mean height of this particular type of dolphins is 14.6 inches with a margin of error of 1.5 inches. What's the most appropriate conclusion? 14.6 inches is our estimate with a margin of error of 1.5. So what does that tell us? 14.6 plus minus 1.5? 13.12? 15? No? 16.1. It's likely to be between this interval. Okay. Let's look at the options now. Let's look at the options. Can all of you read the options and let me know which one seems correct? C? Right? It's plausible that the mean height is between 13.1 and 16.1. Remember, we are studying the mean height. Okay? We're talking about the mean. And we're saying mean is likely to be between 13.1 and 16.1. C is what matches that conclusion the most. But now let's look at the other options and see why they're incorrect. Why is A not correct? Why is A not correct?
Because the question states that estimating mean, why it just says most.
Yeah, so we're talking about the mean here. The study is about the mean height, and they're saying most dolphins. We're not talking about how many dolphins have a height between a certain number. We're just talking about one single number, and that's the mean number. So we're not talking about most dolphins. So this is not correct for that reason. All dolphins have a height of 14.6? No, there is a margin of error, right? So that's not correct as well. No dolphin has a height less than 13.1. What do you think about that? Isn't that correct as well? Why is that not correct? Sorry? It is still possible that the actual number is outside this interval. Okay? We are saying it's likely to be within this interval, but there is a small chance that it goes outside. So we can't say no dolphin has a height beyond this. And in any case, we are talking about the mean. So even if the mean is within this interval, it is possible that some dolphin has a height beyond this interval. If the mean is just going to be within this interval. Is that okay? So it's going to be C. When you're practicing, you should try to figure out or understand each of these questions why the rest of the options are incorrect as well. And that will help you understand these concepts better. Okay? Especially these theoretical questions, you should look at all the options and clearly you should be able to understand why each of the other options is incorrect. Okay? All right. Now, this is another thing that you need to know about. When you can generalize your results. Let's take an example of this first before we talk about this concept. Let's say you want to study, you do a study of elephants from Thailand. You're studying something about them, their weight, their height, or anything else, right? If your sample is elephants from Thailand, you cannot conclude from that it applies to every single type of elephant in the whole world. You have only taken a sample in Thailand. You can only generalize that to elephants in Thailand. Okay? You cannot say that elephants in Pakistan would behave the same way. Okay? Unless you have taken elephants from Pakistan as well. Okay? So if you want to make a conclusion about a set of population, that should have a representation in the sample as well. If you want to make a conclusion about elephants in Pakistan, there should be some elephants from Pakistan included in that sample as well. Otherwise, that conclusion would not be valid. Okay? Now, you're doing a study about some pilots. And in your sample, you only have pilots who are more than 45 years old. You cannot apply the results of that survey to pilots who are below the age of 45. If your sample only includes older pilots, you can't say it applies to all pilots. If you wanted to apply to all pilots, your sample should be random. So it takes pilots from all age groups. Is that okay? So results of any population, any survey can be applied only to the population from which the sample was drawn. Okay? You can't generalize that to the whole world. That's not allowed. That's not valid. Okay? Let's take an example. A real estate agent randomly selected 50 houses in Malden and estimated the mean house value is $750,000. With a margin of error of $80,000, the agent wants to reduce the margin of error. Which sample would reduce that? I'm sorry, this. Okay, it's not about generalizability. We'll look at another example of that on that later on. It's another concept. So choosing a sample. How do you choose a sample? So remember, your results are going to have a margin of error, right? They always have a margin of error. Now, your results are going to be more useful if the margin of error is low, right? So, for example, if you do a survey of who is going to win those elections, now, if your result is saying there's a 35% chance of one party winning with a margin of error of 30%, that's not very useful, right? You're saying it's likely to get 35% votes, this one particular party, but the margin of error in the study is 30%. That means it could be from anywhere, from 5% to 65%. Is that very useful? It's not. So you want to have the margin of error as small as possible for your study to be useful. Now, how can you reduce the margin of error? Let's have a look at this example and try to understand that. There's a real estate agent who randomly selects 50 houses in this city and estimates that mean house value is 750,000 and the margin of error in the study is 80,000. So it's going from 670,000 to 830,000. That's the mean house value. They're saying it's likely to be between this interval. Now you want to reduce this margin of error. How can you reduce the margin of error? They're saying select 30 randomly selected houses in that city, 80 randomly selected houses in some other city, 80 randomly houses in Malden and 100 randomly selected houses in one neighborhood of Malden. What do you think? Sorry? Margin of error was 80,000 plus minus 80,000. Okay, now let's exclude some options. It says 80 randomly selected houses in Massachusetts. Now, does that make sense? We are doing a study about this city. It has nothing to do with this other city, Massachusetts, right? So that's not possible. Okay. What about the last one? 100 randomly selected houses in one neighborhood of Malden. So what would be the problem with this? It's still in Malden, isn't it? Shouldn't that work? What's the problem? You cannot generalize this. So you're doing a survey in Lahore and you want to study something about the level of education that 20-year-olds have in the city. And you select a sample from DHA. Does that make sense? Yeah, so you can only generalize that sample to DHA. You can't generalize that to whole Lahore. So you can't select a sample from one neighborhood and generalize that to whole city. That's not possible. That would not work. So this last option is also incorrect. Now the other two options are select 30 randomly selected houses in Malden or 80 randomly selected houses in Malden. The original choice was 50 houses. The greater your sample size is, the better your results are going to be. So larger samples are going to mean smaller margins of error. Okay? So let's say you have 100 people. You want to study something about those 100 people. If you take a sample of 10 of those people as opposed to 50 of those people, a sample of 50 people is going to be more helpful. It's more likely to be closer to what those 100 people think. Okay? Is that okay? Larger sample sizes mean better results, lower margins of error. Okay? So which option is going to be correct then? C, increasing the sample size is going to reduce the margin of error. Okay? So generally, when you're doing any study, you want the margin of error to be as small as possible. One way to do that is you take larger sample sizes. So you want to take as large a sample size as possible. Now, if larger sample sizes mean better results, why don't we just take a very big samples, do a survey of all houses? Can't we just do that? If larger sample sizes mean better results, shouldn't we just ask every single house what their prices, or study every single house in the city? That's going to give us the best results, right? But it's not practical. It's going to be very expensive. You can't have all of that data from the whole city. So that's why sampling is necessary. But still, you want to have a sample size as big as possible that's not too expensive or not impractical, right? So within your constraints, you want it to be as big as possible, the sample size. So one thing that affects margin of error is sample size. That is something that is in your control, right? You can take larger samples. That would mean smaller margin of error. Okay? Smaller sample sizes increase the margin of error. Now, the other thing that affects margin of error is not something that is in your control as such, and that is the variability in the population. Now, what does that mean? When you were doing that study of house values, let's say the sample that you took, the values were between 100,000 and 800,000. So the sample was very variable, right? The house value was going from 100,000 to 800,000. As opposed to another sample that only had house values from 700,000 to 710,000. Now the first sample has much more variation and the second has much less variation. So the conclusion that you get from the first one is going to have a higher margin of error, and the conclusion that you get from the second one is going to have a low margin of error. Now that actually depends on the actual data. It's not something that you can control, right? It is what it is. When you collect a sample, the data itself could be more variable or less variable. If it's more variable, your results may not be that accurate. If there's less variation in the actual data, your results will be more accurate. Is that okay? Does that make sense? So you can think of it logically as well. If you do a survey, most of the values are between 700,000 and 710,000. You can say it more confidently that the actual value is going to be somewhere between that range. But if it was this, and the mean was coming out to be 450,000, there's going to be less confidence here because the actual house prices are much more varied here. Okay? All right. Any questions until now? No? All right. Now you will have scatter plots sometimes as well. Looking at the scatter plots, you should be able to figure out the relationship between two variables. Now data can be of two types. You can have univariate data. Univariate means one variable at a time. Okay? For one variable data set, you can do visualizations like bar charts or, for instance, box plots, right? What we did in the previous topic, bar charts, box plots. If you have bivariate data, that means two variables in particular. Now, for two variables, you need two axes, right? One x-axis and one y-axis. Scatter plot is one possible visualization that shows you relationship between two variables. Okay, scatter plot. This is what a scatter plot looks like. You need to be able to interpret what the best fit line on a scatter plot represents. Now, you will not be expected to draw a line yourself, okay, because this is done using something that's called regression analysis that you don't know about for now. You will again study that in your first course in statistics, but you just use software for this. It gives you the result. So on SAT as well, you will have this line given. It's the line of best fit. It's the regression line. Now, the scatter plot shows the relationship between age and weight of 7 infants. A line of best fit is shown. So you can see these points shown here. Now, based on these points, you want to predict the weight of a 5-month-old infant. Now, you can't make that prediction based on these points. You first have to make a best fit line. Okay? Now, the best fit line is generally going to be given to you. So when you make a prediction, you are not going to look at the actual points, you're just going to look at the best fit line. So 5-month-old infant, that means this is 5. We are not going to say that the weight is 14 because there's a point that exists there at 14. That's not going to be correct. You will look at what the best fit line is telling you. This is the best fit line and that's estimating it to be 15, so it should be 15 and not 14. Is that okay? So the line of best fit, it predicts relationship between two variables. It will be provided on the SAT. Okay? You will not have to do it yourself. Which of the following equations best represents the line of best fit that's shown here? Can you figure this out? It's just a straight line. What's the equation of the straight line? What's the y-intercept? 2 point something, right? Positive. That means this is not possible because यहाँ पे negative है. This is also not possible, so it's either B or D, right? Now, the gradients are positive in both of them. So how do we figure out which one it is? You can find the gradient if you want. Okay, sorry. So in the first and last option, the y-intercepts are negative, so they're not possible. It's either B or D. Which one of them it is? B or D. How do you figure that out? Is this gradient less than 1 or more than 1? Sure. Is the gradient less than 1 or more than 1? A gradient, one line is like this. 45 degrees. As it goes 1 unit horizontally, it goes 1 unit vertically. So it's going to be like this. Now, is it less steep or more steep than that? It's less steep. So gradient is supposed to be less than 1. It is going to be B. You can do a calculation using any 2 points, but it's much quicker using this because you know this line has a gradient of 1. And it's clearly less steep than that, the line that you see there. Is that okay? All right. Let's look at this example. Researchers conducted an experiment to determine whether exercise improves student exam scores. They randomly selected 200 students and tracked how much they exercised over the course of a year. So they have 200 students that they have selected. At the end of the year, the researchers found that the students who did more exercise performed significantly better on the same exams than the students who did less exercise. Based on the design and the results of the study, which of the following is an appropriate conclusion? What do you think? Yes? What do you think it is? B? D? So A is saying exercise likely improves exam scores. Isn't that what the study is about? The people who are doing exercise, they're getting better scores. But can we conclude that from this information? It's just two things happening at the same time. We cannot say for sure that it's exercise that is causing their scores to be better. It's just two things happening at the same time. Okay? Let's look at the other options as well. Students who do not exercise at all cannot improve their exam scores. It doesn't say anything like that. Any student who starts exercising more will improve his or her exam scores. Again, we can't be sure about that. D says there's a positive association between exercise and exam scores. Association is the same thing as correlation. Remember, you've done this in O levels, correlation between two variables. It's another word for that, association. When two variables are moving in the same direction. So what they're saying is, researchers found that the students who did more exercise performed significantly better on the same exams than the students who did less exercise. Now, if you're doing more exercise, you're getting better results. If you're doing less exercise, you're getting worse results. That means exam scores and exercise, they are correlated. They have a positive association. But we cannot necessarily say that it's exercise that is causing those exam scores to be better. Now, why is that? I'll come back to this example. For that, we need to understand this concept of causation. To determine causation, researchers must use random assignment. So remember, we talked about this. When you're taking a sample, it has to be random, right? It has to be random. It does not mention that in this example. It does say random, but there's another catch here. Even if they are randomly selecting, you're not sure out of which students they are randomly selecting. For example, we have some students who are doing more exercise, and we have other students who are doing less exercise. Now, generally speaking, if you had some 10-year-olds as compared to 18-year-olds, do you expect 18-year-olds to be doing more exercise or 10-year-olds to be doing more exercise? 18-year-olds generally, right? 10-year-olds would be too young for that, right? What if the people who were doing more exercise, most of them were also older? What if the students who were doing more exercise, what if most of them were also older? And these were younger, the people who were doing less exercise. Now, if you have older people, 18-year-olds and 10-year-olds giving the same exam, who do you expect to do better? Generally speaking, older kids are likely to do better. So is it impossible that the exam scores are actually improving because these are older kids, these are younger kids? And it's not because of exercise. So there could be some other variable which is hidden from this situation, which is actually causing that change in your dependent variable. So in this case, the marks are increasing, the exam scores are increasing, and we're just given that people who do more exercise are getting more scores. But it's also possible that those people who are doing more exercise, they're also older. And it's because of their age that they're getting better scores, because maybe they're in higher grades and the other people are in lower grades. Is that okay? So we cannot conclude that it's exercise that is causing better scores. We can just say there's a positive association between exercise and exam scores. They're positively correlated, but we can't say for sure exercise is causing better scores. Because in that case, we could also say the other way around. Better exam scores are causing exercise, causing more people to do exercise, right? How do we know for sure, right? So this is important. Difference between correlation and causation. They are not the same thing. Okay? Difference between correlation and causation. Correlation has another word as well that we use, association. They both mean the same thing. Is that okay? So this is what we discussed. Imagine the researchers assigned all students over 15 to the more exercise group and all students under 15 to the less exercise group. The more exercise group performed better on the exams. Now, how do we know? Was it because they exercised more, or was it because they were older? Right? We can't say that for sure. So unless we do random assignment and we have equal numbers from each set of groups, each set of people, we can't know what it is exactly that is making that difference. Okay? Any problem with this? Now, last thing that you need to know from here, association types, correlation types. Positive correlation is like this. As you go from left to right, the graph is going upwards. Negative correlation is like this. As you go from left to right, the graph is going downwards. Okay? And you can see in this case, as one variable increases, the other is also increasing. In the second case, as one increases, the other is decreasing. So that's a negative correlation, negative association. So positive association means as one variable increases, so does the other. Negative, if one increases, the other decreases. That's a negative correlation, negative association.